Hello, good afternoon, and welcome to another Big Data London webinar. Today we're talking about smarter AI with analytical graph databases. So I'm Andy Steed, Content Director of Big Data London, and I'm joined today by Victor Lee from TigerGraph. Hi, Victor.
Hello, Andy. Hello, everyone.
So these sessions are designed to be interactive. Please ask your questions at any point using the question box at the bottom of the screen, and I'll endeavour to ask as many as I possibly can to Victor at the end of the session. Just a quick note of housekeeping. If you lose the stream at any time, you shouldn't, but if you do, just hit refresh in your browser and you should jump straight back in. Okay, so without further ado, I'd like to pass over to our featured presenter today. Over to you, Victor.
Thank you, Andy, and thank you to everyone for joining us here today at Big Data London. So as he said, I am here to talk to you today about smarter AI with analytical graph databases with some best practices and case studies. So I'm Victor Lee. I'm head of product strategy and developer relations at TigerGraph, a graph database company based in the United States, but we have offices throughout the world, including in London and in Europe. So this is just a little warm-up quote from Gartner, the technology analyst firm. They said last year, graph analysis is possibly the single most effective competitive differentiator for organizations pursuing data-driven operations, etc. So the single most effective competitive differentiator, that is, if you want to stand out in the crowd, if you want to excel and beat the competition, you should be doing graph analysis. And what is graph analysis? So that's what we're going to talk about today. So we're going to start off by giving a little bit of background for those who may be new to graph databases. What's a graph database? And then what is an analytical graph database? And then the title is Smarter AI, so we have to connect this to AI. So why would you want to combine graph and AI? And then I'll give 3 basic approaches for doing so with some use case examples. So types of graph databases. There on the left, I've got a small illustration, a conceptual diagram of graph data. So when we say a graph, we're not talking about, and it's not the picture itself as, you know, it's not a chart showing bars. It's not a bar chart. What it is those circles and lines. And there are 2 major types, the semantic knowledge graph and the property graph. So a semantic graph is a collection of facts. So for example, one fact is a customer resides at a location. That has a subject, a predicate, an object. That connection with the 2 endpoints is one fact. It's called a triple. And in addition, you can also have an ontology, which is a model. So it's defining some concepts and some relationships or rules connecting those concepts, which helps you to interpret that data. So that's the semantic part. So you have these raw facts, and then you have this ontology, which gives some meaning to those facts. And then what can you do with that? So you have this collection of knowledge. You can run queries to search for particular patterns, pattern matching, or you can see how those facts are related to one another and do logical inference. And RDF is a standard, and there's a couple other related standards for the ontology and for the querying. So that's one type. Another type is the property graph, where you focus more on these circles, the nodes, and the lines connecting them, the edges. And those are 2 different types of objects. If you're familiar with object-oriented programming or object relational modeling, or even entity relationship modeling, you understand the concept, nodes and edges. You can also do pattern matching. But the key is you get higher performance if what you want to really do is analytical type. So not so much logical inference, but more conventional database work, or and now we're getting into the AI. If you want to do machine learning type of advanced analytics, you're going to get higher performance on a property graph because of the way it's implemented, the way it's designed. So, and then there are two flavors. You can either have one that's schema-free, it's like not having an ontology to begin with, or you can have one that's schema-based. Traditional relational databases are schema-based. You define your data model first, and then you load data into it. And the advantage of schema-based is it enforces your model, so you know your data is cleaner, and it also allows you to, again, to tune the performance, because when you have larger amounts of data, and when you want to do this more advanced analytics, which is computationally intense, it's important to have high performance. So that's a reason why a lot of people who started with a semantic knowledge graph and were just sort of looking initially at, say, well, what do I know? As they migrate to more analytical use cases, some of them are starting to migrate towards property graphs. And then among that, there are two types. Again, from traditional relational databases, you know, transactional, where it handles updates to the data in a very guaranteed way so that one update does not interfere with another. And, you know, banking institutions will want transactional databases. And then there are analytical databases, which, again, more focus on the performance of doing and analyzing the data holistically. And then there's some that can do both. And my company's database, TigerGraph, we are a combination transactional and analytical property graph database. So that's laying some groundwork for what is a graph database and what's an analytical graph database. Now, why would you want to do this? What does this have to do with AI, and why would you want to combine them? So first, when you model your data as a graph, instead of modeling it in the traditional tabular way, those connections are now so-called first-order objects. They're just as important as the nodes themselves. So those connections are information. So, and you can have many connections, essentially an unlimited number from one entity to another. And if it's implemented as a graph database, those relationships are very efficient to traverse or cross. So you have richer data because you're not just having isolated facts or objects, you're seeing how they relate to one another. And it's also very naturally breaks down your data silos. What is the challenge when you have data in different data sets and you want to somehow merge them? Well, you can very simply just connect things that are supposedly the same or that are related to one another. You can still have graph 1, graph 2, and then you just establish some connections between them, and now you have one graph. And so once you have this, then you can start to ask deeper and smarter questions. As we already talked about, those semantic relationships, whether you're formally using a semantic graph or you're using a property graph, in both cases, your edges can represent semantic relationships. And you can ask questions that relate to the sort of very natural human questions of how is this related to one another? You're thinking about where does this person reside? Where do I ship this to? How are they purchased? And the idea is not to ask just about single connections, but to ask them in chains and in combinations, which in your regular natural human language, such as English, you can very easily express something as, let me know which orders from customers living in this area were purchased in this month, but have not been paid for yet. And in that question, you've maybe expressed 4 different relationships, which writing that in SQL might be challenging, but understanding it visually would be in this graph form is actually quite easy. And then it becomes actually easier to write in the graph query language because you can picture it, you can see it. And then next that moves on to computational options. Graph algorithms. Mathematicians and later computer scientists developed dozens, hundreds of different graph algorithms, which which tell you very specific, interesting things about your data. And they did this sort of in their ivory tower. And now that graph databases are becoming practical and used in the business world, now they've really found their use. Now we can apply these graph algorithms to answer meaningful business questions. And as machine learning has become really big, people have been combining the two. So now there are machine learning approaches which either use graphs to prepare the data better, or to actually intrinsically use graph during the learning process. And that's what I'll be talking about later. And finally, as we talked about how the modeling is more semantic, you can combine those machine learning approaches and the graph approach to give you explainable results. One of the drawbacks of deep learning that we've all heard so much about recently is that it is this black box. And it may give you some wonderful model, but it is actually not very good at explaining why that model works. If you use a more graph-based approach, you do have the potential of leveraging the semantic modeling, which we all understand. If you base your model on the graph structure, then when you get the result, you will also have a more explainable result because it refers to those semantic edges and semantic node types that you have. And lastly, it's a very visual model. And so when you have your machine learning result and it has that explainable model, you can also visually display it that you can easily communicate to less technical audiences. So richer data, deeper, smarter questions, more computational options, and explainable results. And I said I would connect this to some real world examples. I have 3 categories of cases taken from actual customers of ours. One is healthcare. As you may know, in the United States, we don't have a national healthcare system. It's mostly private. It's a very complex and messy system, and to optimize it is challenging. And there's a lot of commercial interest in each organization trying to optimize it. So one of the largest health insurance businesses in the US has built what they call their graph brain. They've taken their massive amounts of data from different, originally several dozens of different data sets, and combined them into one large graph of 1.3 terabytes. And they're using this. They foresee many, many applications, but the first one they're using is to improve their care recommendations by finding how, looking at the surrounding connections, one can understand a patient's situation better. So the graph model, it gives what you call a 360-degree view of seeing all the things that relate to this patient. Once you find a patient of interest, you can search for other ones that are related, have a similar neighborhood. And doing this kind of recommendation is allowing them to provide better health care more quickly, so the patients are getting better care, and the company is able to do it at lower cost because they're seeing these relationships much faster, and they're finding more of them than they ever saw before. A second case is industrial supply chain, and using the graph not only to observe and model the supply chain. You can think, whoa, a supply chain, that is a graph, right? But if you can really make a very rich supply chain that contains this supplier contract terms, product options and variations, the logistical issues, and sales forecasts and orders, to make so-called smart supply chain. And our one customer, Jaguar Land Rover, by upgrading their supply chain to a TigerGraph database with analytics, they reduced their time to run a simulated situation from 3 weeks to 45 minutes. It suddenly became something where they could try multiple options in a day. whereas previously they could only try one option per month, and it really is not viable as a predictive tool. But now it becomes something that they can use to optimize and simulate and explore different scenarios. So they're able to do both tactical and strategic decision making, saving them, again, tens of millions of dollars per year. And third, financial services. We have real-time fraud detection. Again, this one institution in the United States, which sells a lot of tax preparation software and also financial accounting software to millions of customers. They're able to integrate multiple platforms that they have, and it's, again, what their technical officer described as a magical real-time visual result for fraud investigators. So Graph is a wonderful way of connecting the dots. It literally is connecting the dots. And when you are doing some type of investigation, that is what you're trying to do. You're trying to find the less obvious connections, perhaps predict connections which the graph isn't even showing yet, but the surrounding data is telling you there perhaps is a connection there. These are leads that fraud investigators or criminal investigators can use. And so for this firm, this is, again, providing substantial benefit for catching more fraud more quickly. So now I'm going to go more into each of the three cases of how can you use Graph for smarter AI. And the first is using analytical queries and graph algorithms. I previously mentioned there are lots of types of graph algorithms, such as pathfinding, clustering your nodes, or community detection. The cluster is a community. Ranking or centrality, so which nodes are the most important or which nodes are the most centrally located. Similarity, that's like in the healthcare example I just talked about. Which nodes are similar to one another based on their situational or structural characteristics. And then what patterns? A pattern is maybe a small collection, a small connected group of vertices. They're connected in a certain way, and there's certain types of nodes and certain types of edges, and they represent a pattern that you see over and over again. Where are those? What are those frequent patterns? There are a few other types of graph algorithms, but I'm just covering these as an examples. And these are all, again, things that are specific to graph, and they're all telling you useful information which you can apply to the real world. And the ones that I have in bold are indicative ones that are a little more complex and that you might consider as unsupervised machine learning, where you're not giving it any training data. You haven't labeled any cases of interest. Particular, you think about frequent pattern discovery. I don't know what pattern I'm looking for. Just tell me what pattern is very frequent. Or similarity, you simply say, I have this one reference node. Tell me what other nodes are similar to it, based not just on that node's properties, but on that node's connections to other nodes. And now, again, get into some more specific case examples, again, in healthcare. So suppose you have a network of doctors who provide care within a system, but they're connected not only by some formal business relationship, but because they will make referrals. And referral in the sense you start seeing a general physician, and he sees you have a particular type of problem, and he refers you to a specialist. And so this type of referral, we're trying to see, well, who is the most influential specialist in a particular region for a particular area? And how would we do that? Well, one graph algorithm, which is designed to measure influence, is PageRank. PageRank was used by Google in its early days to rank web pages, which are the most important or influential web pages. And the same algorithm can be used here because it's a referral network to see which medical provider is receiving. It's not just the number of referrals, but the most important referrals. Well, which referrals are important? Well, it depends on who made the referral. And so if you are influential and then you refer to another person, your referral matters more than a referral from a less important. So it's this self-looping or recursive pattern. Influence builds on other influence. So anyway, that's the PageRank algorithm. So a graph algorithm being used to answer a healthcare, or you might think of it as business question. And then we have a follow-on question. Who is influenced by these leaders? Who are they influencing? And then we can use a community detection algorithm to define the group boundaries. And it's, again, not necessarily direct, doesn't have to be direct connections. It can be a connection of a couple steps, but it's based on the density of connections. If this is a well-defined community, if there are lots of connections within the group, and then much sparser connections going out of the group. And it's a relative measure. You have to, it depends on the data itself, what is considered dense, what is considered sparse. But both of these, PageRank and community detection, are graph algorithms used in combination to answer this meaningful business question. We go back to, here's a different case using a different type of graph algorithm. And this goes back to the similar patients I talked about. This is a visual display of the, you might call the medical healthcare journey of this patient, Doris. There are different parameters of her healthcare, and this is a timeline, and you can see she's had all these different interactions with the system. And there are a couple situations that are flagged as cautions. Maybe there was a negative report, or maybe she missed an appointment. And so I am interested, this patient should receive some special attention. Who else should receive this special attention? You simply click this button, find similar members, and in a matter of a second, it will report out of the many millions of patients. And this is based on a real system, as I said, in operation. How many other patients are in a similar situation? It will give you a list. What does this have to do with a graph? Excuse me. Well, let me show you how it's implemented underneath. They are using their graph brain, as we said, and we have at least two types of nodes. We have the patients or persons, and we have their interactions with the healthcare system, or so-called features. And so each person is connected to some features, and we see here that person A is connected to feature WXY, person B is connected to feature XYZ. They have features X and Y in common. So they have 2 out of 3 each in common. Plus there are also these numerical weights saying how important is this, or how strong is this connection. And so there are several different algorithms you could use, several different measures, but this measure that they're using is called cosine similarity. And so it takes these weights and it counts the connections, etc., and you come up with a score. And basically, the pairs of patients that have the highest score are the most similar. And so this is actually a graph problem that they're solving, and they're doing, again, millions of these comparisons in under a second. And finally, to show one more way that we can answer important real-world questions, in this case, building on top of those similarity scores. And this question is so-called entity resolution. In a data set, you may have multiple virtual or digital entities, which in fact represent the same physical entity. For example, I have several email addresses. I have one at work, and I have multiple personal email addresses. So there's several virtual entities, my email addresses, which all refer to me, one physical person. So entity resolution is the problem of trying to figure out, if I don't tell you, how do companies guess that all of these email addresses all refer to me? Well, they look at what properties they do know. And for example, you have these 7 entities, and presuming that they've looked at these surrounding properties, just like we did in the previous example, and come up with similarity scores. So then we could join these different entities, which ones have relatively high similarity scores. You see some in the 90 percentages, 89, that's still pretty high. And then we see these that are only about 60, 65% similarity. So it's lower. And we even completely ignore the ones that are very low. So these are all the ones that are moderately high. And then we just filter for which ones are the strongest. So you see, we decide, oh, these are in the 90s or 89 or higher. That's very strong. These are probably the same actual person. And these are the same actual person, but the separation between these two was in the 60s. So we decide that's a difference. So we resolved those 7 entities, those 7 digital entities, into 2 hypothesized real-world entities, and we have something like a 90% confidence that it's true. So now we get into a second use case. So the first use case was using graph algorithms and graph queries to do unsupervised learning. And the second use case here, excuse me, is using graph feature extraction. And in this case, the features are going to be for preparing for supervised machine learning. In supervised machine learning, you label some data as sort of the target result, but you also need to know some things about the data, which are called the features, or the properties or attributes. So if I know these things about the data, and then for some of them, I know what target result I want, then you look at the pattern of, I see these features correlate with that result, and by running one type of algorithm, such as a neural network, to continually observe that data until you can thread out a model, so to speak, of we assume that these features in this way with these weights result in that target result. So what you're trying to do is, what are the features that are going to help you make that prediction? And you don't know in advance. That's the challenge. You don't know which features matter. But in general, the more features you have to start from, the better, and the more meaningful features you have. So what we're saying is, your graph can provide you not only more features, but some more meaningful features. So, and also, as we'll talk about, explainable features. So this is, again, one of our customers, China Mobile. And now many of you may have a system where your phone service provider will screen a phone call and tell you if it's an unwanted call. And so this is one of those systems, but this was introduced 5 years ago. This is one of the first such systems. And what they did is they constructed a so-called phone call graph, where each node is a telephone and each edge is a phone call, and they collect the historical data. They have hundreds of millions of customers. They receive billions of calls per day, many billions per month. So they took a subset of their data over a 2-month span, and they had labeled some as known unwanted calls. But at this feature extraction stage, what they're looking for is, let's look at the pattern of phone calls surrounding, this is phone number 1, the caller. And you can see, for example, this pattern is called a stable group. Caller 1 calls these people on a regular basis. And what regular means is some tunable parameter, but it means you call them on a regular basis. That's a stable group. Now take a stable group and say, do they call one another? And if they call one another, then you have an in-group, and that's another feature. And sort of the size and how many people and who's in this group and its size are more characteristics of the feature. And then you can have a feature like this where one calls two, two calls 11, and one also calls three, and we close the loop with 11 calling 3. So are there relatively short loops like this of 3 or 4 callers? And again, what is that saying about all of these target people are sort of in the well-known safe group? And China Mobile, together with TigerGraph, actually constructed 118 of these semantic features. Notice all of these features have some meaning. You can describe them in terms of telephone caller behavior, which has some real world meaning. And so they extracted these graph features. They can run them as a query for a particular node. They can extract all the features in a fraction of a second. And what they did, they trained their data, 118 features. They had 3 types of unwanted calls. They used a training set of 30 million calls, representing a subset of the data collected over a month. And they came up with a model, actually a decision tree, which could identify these 3 types of calls. And again, they could process one TigerGraph machine could process 2,000 calls per second. If they just put more machines in parallel, they could, double or triple. However machines they run in parallel, they could handle that many more calls. And then they can retrain the system periodically because the unwanted calls are changing the behavior regularly. And so, and again, it gives you the result in fast enough that as you, the person receiving the call, will see the alert before you choose to answer or not. It'll tell you if this is a salesperson, a solicitor, if this is actually somebody who's committed serious financial scams in the past. And again, this model has the potential for giving you explainable AI. So you start with these graph, and you extract your graph features, and you use those graph features to train the data. You come up with your model. And remember, all of those 118 features had some semantic meaning. So the model will be expressed in terms of these things that we can understand. And lastly, we come to a third type. So again, first type was graph algorithms for unsupervised learning. Secondly, we have in graph features to enrich the training data. And third, we have actual in-graph database machine learning. So this is a really nifty model. First, you build your graph. Again, we talked about how graph can break down your data silos, connect all your data, provide you a 360-degree view. You then enrich that data with the graph feature extraction that we just talked about, plus any other. You had some features already, and you enrich it with additional graph features. Now you run an in-graph supervised machine learning training model, and we'll go into some examples of that in next. But so the data is still remaining within the graph, and so now you have a graph database which has been trained in place, and then so you don't have to, you can again deploy it right there. So to do this, you would want a so-called native graph, because this is going to be computationally intense. So you want to pick a graph which is going to perform well computationally. So a native graph database. An advantage of this is that you only have to express develop one graph, and it can also automatically scale out and scale up without having to redeploy. Our TigerGraph also has the advantage of we have real-time updates which not every graph database has. So that means as the data is changing, for example, in the China mobile case, every time a new phone call comes in, that is actually adding to the graph itself. So not only are you requesting you're requesting the model to tell you, is this a good or bad phone call, you're actually also updating the graph itself. And lastly, TigerGraph's query language, GSQL, is so-called Turing complete, which means that you can express algorithms in our query language. Not all graph databases are designed for this analytical workload, but our query language has the capacity to express these algorithms. It can do it quickly and efficiently, do the native graph and parallel processing, and the database is distributed and it can scale out. So as the amount of data increases, you can still stay with the same platform and increase without having to move to a different system. So here's one example of in-database machine learning, common example of movie recommendation. So we have some data describing a movie, and we have some reviews of the movies by persons and their ratings. And this whole example that I'm going to describe is in one of our webinars. You can look for it as Graph Gurus episode 28, low rank approximation machine learning, and it also comes as a starter kit on TigerGraph Cloud. So if you want to see this example in more detail, you can look at one of those. So over here, I'm highlighting the movie features, the rating, the release date, the director, the genre, also pointing out the users and the ratings. So I have 3 types of data, and turns out we can model the movies as nodes, the movie features as more nodes, the users as nodes, and the ratings as edges. And the goal, what we're trying to do is we're trying to predict movie ratings or predict whether someone would like a movie. They have not seen this movie yet, but based on what we do know about their taste, would they like this movie? And so we build this user rating movie graph. So we have the movies with their features. We have users and things we know about them that they've described about themselves or things we've inferred. And we have the ratings we know. We know Alice gave a 5 to Toy Story. We know Bob gave a 5 to Iron Man. But what would Alice think of Iron Man? So we're trying to predict a rating. So we trained this on the Movie Lens data set. It's an open source data set, 100,000 ratings, 40,000 tags, 1,000 users, etc. Each rating is from 0 to 5. And there's several possible approaches you could use, but we used the latent factor model. And you think about this, and this is similar to a neural network in that you have a hidden layer. So this is the data we know. This is we know the users, we know the movies, we know the ratings, and notice that this is like a matrix, and it could also be represented as a graph, as we saw in the previous page. But there's some missing ones, so that we don't know what the value is there. These are like the missing edges. But what we've done is for each user and for each movie, we have, by studying the data, by some data preparation steps, which are explained more in the webinar or in the cloud TigerGraph Cloud Starter Kit. It gives more details about how we come up with these intermediate values. But we've basically categorized the movies into 2 cases. For example, this is just an example, romance and action. These were the features we knew. And that represents sort of the intermediate stage. And so again, each person is characterized by those features, and each movie is also characterized. And then you can do some matrix multiplication to predict these ratings. So and the model actually tells us, this was the actual rating was a 5. The model tells us it would be a 4.5, which is close. This one, it got exactly right. Again, close, exactly right. And this is the important part. This is where it predicted that Alice would strongly like Cute Puppies of Love. Alice would not particularly like Toy Story. And so that is one type of graph model. There are more graph machine learning models. There's several more. I'm actually working on a longer work to describe all of these. So if you pay attention, if you follow TigerGraph, you'll find out more about our work in graph plus machine learning neural network models. One we're going to take a quick look at is called the graph convolutional neural network. And very quickly, if you know how basic neural networks work, this is a quick backgrounder if you're not familiar with neural networks. You have the input layer. You could think of these as, again, the nodes that we know in our data. And the output layer, these are the predictions we're trying to make. So in the case of, for example, the China mobile case, these would be all the phones, the millions of phones are the input layer. The output layer are the 3 types of fraud, 3 types of unwanted phone call that we're trying to predict, plus the okay phone call. So 4 cases, 3 unwanted and 1 acceptable. And these hidden layers are imaginary variables which help to predict from the input data what is the output data. And these connections, you basically establish a connection from every node in the previous layer to every node in the next layer. It's a mesh of connections. And you start off also, each connection has a weight. And what we're trying to do is learn what are the correct weights such that if you follow the steps going from the input through the hidden layer, through another one, etc., you will end up with the correct scores, which one has the strong signal. It should select one of these as having a strong value and the others having a weak value. If you have that's the prediction. With these inputs, I predict that output. You start off with some random weights. You iterate the algorithm. You keep running this cycle repeatedly and keep updating the weights, and eventually it converges on the correct weights, the model. That is the model. The model is the weights. So that's a conventional neural network. A multi-layer one like this that's deep learning. If it was a single layer, that would not be deep. Multiple layers is deep learning. What a graph convolutional network is, it's not really shown here, but I've actually introduced another step here. If you go back here, and we talked about how this matrix is actually similar in concept to this graph, then we can call this an adjacency matrix. Everywhere there's a value represented a connection in the graph. Everywhere there is not a value there is no connection. So this matrix is a representation of a weighted graph. It's an adjacency, it's a weighted adjacency matrix. And that is what this variable A represents. Variable A is a weighted adjacency matrix. It is the graph structure. What we're doing is we're taking a traditional neural network process and we're multiplying, adding one additional step. So again, without it, with it, we're multiplying the adjacency matrix by the set of connections, by the layer itself. And so we're adding in the connection pattern to say each node is influenced not just by, again, what we did before, but it's influenced by its neighbors. The adjacency matrix is basically connecting you to your neighbors. And so it's saying each node is influenced, it's not just a standalone entity, but it's connected. These graph connections exist, they matter. And that is basically the graph convolutional network. And I'm about to wrap up again. So again, I will go over what we've learned, but why this is really important to TigerGraph is because as in the graph database market, we distinguish ourselves by our parallelism and speed, and this is really a very good fit for this graph plus AI. So first of all, the real-time deep link querying, of the ability to traverse much more deeply in the graph in the same amount of time with the same amount of resources. So it's much more efficient at traversing the graph and at updating it. The massively parallel processing allows you to handle more data efficiently. And again, all this machine learning, it's built on big data. The more data you need a sufficient volume and sufficient variety of data to do efficient artificial intelligence and machine learning. So TigerGraph can handle that. And again, our query language is able to express and handle these algorithms. You don't need to wait for TigerGraph to update its product to provide a built-in algorithm. Algorithms can be written by anyone who becomes a strong practitioner in the G-SQL language, can implement a graph algorithm themselves, or hire someone for services. But the thing is, you don't have to wait for us to build it into the product. It's generically available because you can just write algorithms in our query language. And again, to appeal to those who do not have quite maybe that level of sophistication, you can do analytics without writing any query. When I showed you the graph patterns used for graph features for China Mobile, you could describe those patterns using our new visual query builder, where you just draw the pattern on our Graph Studio, and without having to write the code, it just infers from the pattern that you drew what is the pattern you're interested in, and writes a query to search for that pattern. So lastly, just summarize what we've talked about. Graph is a wonderful natural data model. Graphs are thinking in terms of these objects and relationships. It's how we think. It gives you a richer data. All those connections add multiple dimensions to what you can represent. And so they have a natural role in machine learning. First, for unsupervised learning with graph algorithms. Second, learning through neural networks and deep learning. And third, the graph features provide you with richer training data. And those graph data models are uniquely qualified to provide more explainable AI. And lastly, natural graphs or native graphs with massively parallel processing, like TigerGraph, are the ones that are suited to do this in-graph analytics. Again, some of the examples I showed you today are available on TigerGraph Cloud. You can just go to tigergraph.com/cloud to find out more. If you are a developer and want to try some things on your own, you can go to dev.tigergraph.com, and you can also see some more examples that we have. Again, so you can try out TigerGraph Cloud for free. You can go to learn.tigergraph.com to do some free training on G-SQL and using the TigerGraph platform in general. You can go to our online community to discuss. And I said we're US-based, but we have sales and support right here in Europe. And my colleague, Deborah Ives, has asked me to invite you to contact her directly. So Deborah would be happy to hear from you. And we, of course, are on social media. So I want to thank you for your time. Thank you for your patience. And if you have any questions, I would be happy to take them now.
Thank you very much. Thank you very much, Victor. Yeah, we've got some good questions. I'll try and get through as many as I possibly can. So thanks for sending them in, and do continue to do so. I'm going to go for the one that's cropped up latest, actually, first, as top of the pile. You say that the technology is computationally intensive. What sort of hardware or cloud infrastructure do you need or do you need a complex or intensive cloud infrastructure without going into vendors, perhaps, to run
Sure.
sort of databases?
That's a great question. One of the great things about TigerGraph is that it can, first of all, it does run on the Linux operating system. So I do have it running on my laptop using a Docker. So I have TigerGraph running on my MacBook, running within a Docker virtual machine. So it will work on just an ordinary laptop. The only thing is you'll be limited in the amount of data and processing power. We have it, and it really also we compress the data so that we can fit 4 to 10 times more data than some of the competing graph databases. So that's a help. We have some recommendations based on how much data and what type of workload you have, but you really can start from fairly modest sizes. I said we have customers who have a terabyte or 10 terabytes of data, and they obviously have several machines, but it's all what we consider commodity hardware. You don't need special CPUs. We recommend solid state drives, but it's not an absolute requirement. So nothing exotic is required.
Good. Are the slides available? So this session is available on demand almost instantly as we finish. So you'll be able to watch it again, forward, pause on Victor's presentation and catch any bits and his commentary on that bit. So feel free to do that. This is an interesting question. Because most people start sort of tabular relational, is there a pathway to graph, or is it a greenfield project, or is there a way to sort of forward your self from kind of a more traditional standpoint?
Right. We try to make it as easy as possible. So we do have a beta version of a tool called a relational to graph migration tool, where you can take TigerGraph to connect to a relational database. It will read your data model, suggest a graph model for you. You can tweak it a little bit to if you don't like the initial suggestion. And then you have a graph model, and then it will also import the data for you. So you can easily migrate the data. And then the next stage is, well, I've got my data in a graph now. Now, how do I write queries? Again, we've tried to make that easy. Our query language is called GSQL. So we took the name SQL because our syntax is inspired by the SQL query language. Excuse me. It's obviously got a little more hooks to it because you are dealing with graph. And we try to give you additional capability, in particular, the procedural capability, like programmers will know control flow, procedures, variables, so that you have the simple so-called declarative style of SQL, but we've also added the imperative procedural capability around it, so you can write more complex things. So we've got tutorials that try to make it as easy as possible, but those are the two things I would suggest. You got the data migration tool, and then our query language tries to be SQL-like.
Perfect. So the next two questions I'm going to kind of bolt together because I think you might answer one in answering the other one. It's going back to early on in the presentation when you talked about the fact that graph algorithms to a certain extent were developed in this sort of ivory tower academia. I think what the person's trying to get to is if you go ahead and go with something, do they need more people? Do they need different people with different skills? And how available are the skills to make this work? What do people need? What skills do people need?
Sure. So one good thing, a lot of computer science students studied graph algorithms in their university education. It's part of the regular curriculum. They just didn't expect they would necessarily be, they may have not realize this would be useful later on. Obviously, while I said we do have the visual query builder where you can do some things without coding, it is still, you definitely will be able to do more if you're writing code. So somebody should spend the time to learn the query language. Our language, for example. We do have free training courses and free certification courses. So we have a growing community. So more and more people are learning this, including we have high school students. So I don't want anybody to feel bad if this is not their natural talent, but we do have some high school students who have picked this up. The DBA skills are pretty ordinary. I said it is a Linux system. We have the cloud system which then you don't have to worry about administering it. TigerGraph Cloud, you don't need a DBA. You just need to learn the query language. Good computer scientists have learned graph algorithms. There are definitely some best practices. So the great thing about this is I think you can start small and see as the more you do with it, our customers always find more and more applications. So after they make their first foray, then they get comfortable expanding their data, expanding their use cases. So I say the only thing you need to worry about is learning the query language, and we have free training.
Perfect. Okay, perfect. I think I'm going to go on to a last question now, wrap it up. And it's going to be more about communicating it to non-technical people. And we ask this question quite often in these webinars. You're going to the board, you're going for investment, you want to transform. I mean, what sort of things do you need to be saying to them to get them to buy into graph analytics? They may say, we've got regular analytics. I think that's fine. What's the what can you tell a non-technical person what they're going to get their ROI from investing in this?
Sure. Seeing the analytics is all about understanding how things relate to one another and assessing them in that way. And graph is the natural way to explore not just the surface connections, but the much deeper connections, and to learn from that. So graph is giving you much deeper insight, therefore smarter insight into things, which is going to give you better decision making to either cut your expenses, improve your sales, or improve your operations. It's just offering a whole nother level of insight into how to do things better.
Perfect. Well, with that, I think we're going to wrap things up here. Thank you very much, Victor, for a very interesting presentation. Big audience today as well, so I hope everybody enjoyed it. And we'll look forward to seeing you soon. So thank you very much, Victor.
Thank you, and thank you, everyone.
And we'll see you again next week. All right. Thank you very much. Bye-bye.
Bye, everyone.